have connected this before.
Okay.
Try now.
Thank
I
you.
hope it works.
It does. Thank you very much. I'd like to thank the organizers and the PC committee for the chance to talk, and thank you all for being here today. I'm going to talk about a less familiar topic in a very familiar field. The field is protein docking, and I don't think I want to. So the preprint is already posted on arXiv in January, and the codes are also available. So this is my student Yue's housework. So I don't think for this community I have to emphasize the importance of protein docking, because for over 90% of the human protein-protein interactome, we have the dark PPIs whose structures are unknown. So here we really hope that protein docking can help fill the gap. And this can be done through a ab initio or template-based protein docking, but it can also be combined with low-resolution experimental data, as in the last talk suggested, as well as computational predictions. So contact prediction would be covered a lot in the later part of this talk. This 3D-seq. So the less familiar topic is uncertainty. What uncertainty? So life is full of uncertainty, so is the world of algorithms. So we start with a minimization problem. You start with two crystal structures. They are uncertain. And then you start with some free energy model. They are uncertain. And then they do some sampling. They are uncertain. At the end, you get some kind of solutions. You could end up with any of these solutions. And you wonder, well, how much does my model have confidence in any of these predictions, and would it know that it doesn't know something about the space? So that's what we call uncertainty quantification. Specifically, we need to know the distribution of the prediction over the space. So what can you do with this distribution? Well, if you try to sample for each trajectory, for instance, you are refining one model, you will get more robust solutions because you're going to be aware of the uncertainty. The second one is after the refinement of many models, if you do a quality assessment, this is going to help you do better model ranking as well. I will show you later on. So the methods part, let's start with this minimization problem. So the main contribution in this talk is a search algorithm that we iteratively feed between these two elements, posterior estimation and active sampling. But also there are two contributions in the other factors because protein docking is really too complex to be handled by any single factor. So you have to consider the search space, that there is a rigid body motion, there is flexibility. How do you deal with a much lower dimensional space that can anticipate conformational changes, yet still define a Euclidean space friendly for optimization? And secondly, you also have to think about the energy model. So here we constructed a funnel-like machine learning model for encounter complexes. Okay, so the first one and the main contribution is the search algorithm. So the question is, how do you perform uncertainty-aware searches to efficiently locate the global optimum, the native structure, at the same time characterize the uncertainty in the prediction? Okay, so the way we do it is a Bayesian perspective, because really when you are doing protein docking or protein structure prediction, the native structure is unknown. So it's a random variable. So we take a Bayesian perspective and treat it as a random variable, and we are trying to estimate the posterior distribution of this native structure given the data. Okay, this data could be your previous samples or any other kind of information. Okay, at the same time, once you have this posterior estimation, you can use this posterior to guide the next round iteration of sampling, and these two elements can iteratively feed each other. So let me show you one illustration. So this is a very rugged energy landscape whose global optimum is here, so shown by the dashed line. And then in the first iteration, we actually have more or less a uniform sampling because you don't assume any information in the first iteration. And then based on the first iteration samples, you regress the landscape, and which looks like this now. Of course, is far away from its global optimum, is far away from the real global optimum, right? But this is done by kriging, okay? And then this is actually the first time we do the direct modeling of the posterior for the global optimum. This is also inspired by Pedro Ortega's work. So after the preprint, we were happy to see the authors mention that this is really, because in the other Bayesian optimization framework, you actually do this posterior in the functional space, and then for each function in the functional space, you do some optimization. So that two-step process is actually very consuming and not worthwhile, not possible actually for protein docking problem. And then once you constructed this initial landscape, you can use a Boltzmann distribution to construct the posterior. So, and then based on the posterior next round, you will sample more around the peaks. Right? So then in the next round, you see these cyan samples, which are more closer to the peaks. And then you update your posterior. And you keep doing that. And the warmer colors show the later samples. So you see that later samples are more concentrated near the global optimum. And the posterior is getting narrower peaks and shifted toward the global optimum. So over the iterations, you can also ask how the uncertainty has been changed. This can be modeled by the entropy of the posterior. You see that the uncertainty is decreasing over iterations. So the second part is the conformational space. So the central question is, how do you reduce the dimensionality and the range of the conformational space without worrying about all the 3n minus 6 dimensional space, right? So, but of course, you still have to be able to recover the conformational space because proteins are flexible, right? Because in that reduced dimension, you also would like to preserve a Euclidean kind of geometry where the distance between 2 points is simply measured by the line segment. So it's flat. There's no manifold there. And how do we achieve both? Okay? So it wasn't very clear to us until recently that for the first part, it's relatively easy. We have done it before, recovering the conformational changes. This was actually presented 4 years ago in doubling ISMB, that we, for the first time, combined the conformational selection and induced fit into a normal mode analysis. So it's partner-specific and context-specific. Okay? So in this case, we established before that you could use the CNMA eigenvectors to recover the direction of the conformational changes, even if you are starting from a very low quality models, which are basically classified as incorrect in Capri criteria. And you can also combine the eigenvalues with machine learning to recover the extent of conformational changes, because even in the lower dimensional space, you don't want to sample too far away. So both were established before, but it wasn't very clear to us how do you preserve the Euclidean geometry friendly for large-scale optimization problem. So if you take a look at the protein docking problem, when I started doing this, we thought rigid body protein docking is probably simpler than flexible protein docking. Yes and no, because the 3 degrees of rotations are in the special orthogonal group, so the overall 6-dimensional space is a Riemannian manifold. And why is that a problem? Well, imagine projecting a 2-dimensional quadratic functions contour onto this flat Euclidean poster screen versus projecting that to a very rugged and spiky landscape. And then in these 2 scenarios, which one is more friendly to an optimizer's eye, right? So that's the challenge. So over the years, we gradually moved from rigid body protein, rigid body motion, that you can look at as 6-dimensional degrees of freedom and remove the distance and locally approximate these Riemannian manifolds into Euclidean space. And then you consider the flexibility, but you're sort of using the conventional normal modes back then. And this is for the first time that we are able to blend both rigid body motions and flexibility, right, into one framework that you can simply use a set of orthogonal normal modes which capture both rigid body motions and the flexibility. Okay. So if I have time, I can show one very simple. Can't really see the mouse. All right, so in this case, it's probably not very clear, but you have the receptor, which is fixed in space, but is actually flexing a little bit, and the ligand is moving and flexing at the same time. So I would like to ask fellow protein modelers to try out these parameterizations and tell us the remaining gaps we have to fill, because I'm pretty sure there are more remaining gaps to be filled. And the next is the energy model. We didn't spend too much time on this part for this paper, but the idea is like we'd like to have, this is a protein folding funnel, but we'd like to have an energy model that gradually descend toward the native structure, which helps optimization, right? So in the protein binding world, we have thought about it. What if everybody measures the binding affinity of the real native structures, right? There's not an easy way to measure the affinity for the encounter complex, but that's something we sort of needed, right? So we thought about what is the best way to structure that. So we thought that it should be exponential to the alpha of this one, and this IRMSD is like the quality of the RMSD. Then you say, well, when you're doing protein docking, you don't have the interface. How do you calculate the interface RMSD? Well, we don't use the native interface. We use the putative interface RMSD, okay? So this Q is a parameter. So if you take the log on both sides, when Q is equal to 2, this is like a Hookean potential, which is penalizing IRMSD bigger than 0, right? So, and if you take the log on both sides and you have a Y, which is a binding energy, right? So then you can construct a lot of data with known putative interface RMSDs, right? And you can have the binding affinity known, and then you can construct a machine learning model to predict this Y, okay? So that's what we did. But another thing interesting is that if you during the regressing or sampling, you estimated, once the model is learned, you estimated Y, then you can inversely calculate the interface RMSD, which is like a quality assessment estimator. But you can use any quality assessment as well. It's not the focus of this result. So let's take a look at the result. And we're looking at a protein benchmark set, including 176 pairs of proteins. And the training set has 50 pairs. They're only used for training the energy models. So we were not using the training set for other purposes. And there are two test sets. Test set A has 26 PPIs with known KD values. And then there are cases, 100 of them, with predicted KD values, purely from sequence. And then there's also a caprice set, all the heterodimers from 2007 to 2016. I excluded the capri CASP heterodimer targets. And then there are 15 of them, and there are unbound docking, unbound homology docking, and 8 homology docking. All the homology models were constructed by iTaser when the capri targets were released. And all are with predicted KD, and we refine the top 10 models from ZDoc or ClassPro, and more can be done as well. So how do we do? So I'd like to say, before quality assessment meets UQ, you have some docking which does optimization only, and then you have a point estimation of the native structure. You pass it to a quality assessment. Well, I'd like to say that this is a quality assessment in the general definition in CASP. This is a quality estimation when you don't know the ground truth, okay? So it's a quality estimation, actually. But anyway, at the end, you have a single quality estimation of your prediction. So what we do is that instead, you have a both optimization and uncertainty quantification. So the UQ actually gives you the posterior distribution of your prediction, and then you pass it to your favorite quality assessment toolbox. At the end, what you get is you get the distribution of the qualities, right? So if you fix the confidence, right? If you fix the confidence, you will get the range of the quality, right? If you fix the range, you will get the confidence. Okay, so it's very useful. So let's see how we use it. So if you fix the confidence, then you can get the range of the quality, which is IRMSD here. Okay, here you see that I'm varying the level of confidences from 99 to 80%, right? I'm looking at two measures of the predicted range. One is how often your prediction, the native structure is really in the range, right? That's the P part. Another one is your range cannot be too wide, right? How tight is your range? What is the radius, of the range relative to the true label, which is the interface RMSD. So apparently there's a trade-off between the two, right? But basically, if you look at these probabilities, they pretty much match the confidence levels, which shows that these posterior estimations are really pretty good. And then if you look at the trade-off between the two, you can have a good match at 90 or 85% between the probability and the confidence. And the range, okay, with the mean and the standard deviation is not too wide either. So that's the first application. The second application is that now you can fix the range and ask what is confidence. For instance, you can let upper bound to be 4 angstrom. This is what Capri says. This is an acceptable model. Okay, you can predict what's the probability that your model is acceptable. So using this confidence level, so we look at this binary classification problem for all the models. If you just use the MMGBSA sum, you get the AURC about random, 0.5. AUPRC is 0.24. Here, I think AUPRC is a much better measure because native contexts are minorities. So AUPRC is better. And then if you use the random forest, that's what we had, you improve, right? And then if you use our model, using the confidence scores, you see that the improvement is much higher, even here. Okay? So that's the second application, when QA meets UQ. The third application, you can also use these confidence scores not for classification, but the ranking. What about the Spearman correlation between your model ranking and the true ranking? So again, we are comparing the sum of MMGBSA or random forest, and across the benchmark test set or Capri set, you see that the Spearman correlation is much improved, and the variance is slightly smaller compared to this random forest, actually. So finally, when you have this uncertainty quantification aware optimization and the ranking, what we get is that pretty much for top 3 or top 5 models, we can cover 1/3 of the targets, whether it's in the test case or the Capri case, okay? And what about the running time? We actually only sample 600 samples for each model. Currently, most of the running time is proportional to the number of residues, and that can be much reduced as well. And you can visualize the energy landscape now because you regress the landscape, right? So there are more funnels that can be reduced. So in conclusion, for the first time, we quantify the solution uncertainty for protein docking, and you can propagate that solution uncertainty to quality uncertainty. And this quality uncertainty can help you not only classification, but also ranking afterwards. And we also used the complex norm modes, which can anticipate the conformational changes and preserve the Euclidean geometry and the funnel-like energy landscape. And the code and the preprint are available here. And I use, there's a poster tonight at A089. And one more poster to broadcast is, in the last year's ECCB, we used a physics-based protein design algorithm. And this year, we look at the data. How much can you use existing sequence structure data and design a desired fold? And this is probably the second similar work. And we found that our accuracies are similar and diversities are better. This is our posters on Wednesday. And lastly, speaking of interpretable protein ligand interactions, we have developed in the past year some deep models predicting the protein ligand binding affinity, one of the first studies. But here we also embed the joint attention to tell us where proteins and ligand interact and where are the binding sites. And these are availability here. And finally, I'd like to thank you all, and thank you for your attention.
Thank you very much. As we are running out of time and we use the question time to speak about the posters, I suggest that you meet him at the posters for questions.
Thank you.
So now we'll have our final speaker of this session, which is Simon Kello. And Simon, you're going to use your own laptop, or?
Actually, I do have a USB, if that works as well.
It works if we manage to. This is yours?